Okay, so remember our theorem is that, well, it's easier to look at the diagram. Suppose we have the diagram in black. So we have an isomorphism of fields K and L. That's the vertical lines here. It's right here. And we have two simple extensions, one of K and one of L. What our theorem is telling us is if our isomorphism of the base fields sends one minimal polynomial to the other, then there exists an extension of that isomorphism to the simple algebraic extensions that sends the generator of one to the other and is the same as iota on the coefficients. Okay, that's what it says. So let's go ahead and prove it. So let's let K, L, alpha, beta, M alpha, M beta, iota be as in the problem statement. All right. Then the isomorphism J from K join alpha to L join beta can be found as follows. All right. So first of all, we have the isomorphisms. K adjoin alpha with, let me write it the other way. K adjoin T mod M alpha with K adjoin alpha given by evaluate T at alpha. And L adjoin T, mod M beta given by evaluate T at beta. All right, there is a mapping this way. Let me call it J hat as follows. So define J hat by, well, we know we can extend iota hat to be functions from to be a homomorphism from the ring of polynomials over K to the ring of polynomials over L. This is just the change of coefficients function, right? What do we want J to be? Well, if we quotient now by the corresponding minimal polynomials, let's be really precise. I'm going to be super precise here. Then we can quotient on the right by, I guess this is a new sentence, by M beta to get a function f from K join T to L join T mod M beta, where the function is do iota hat and then quotient by M beta. Since iota of M alpha of T equals M beta of T, in fact, we get a well-defined function map J hat from K join T mod M alpha to L join T mod M beta. Why is that? Well, M alpha goes to 0, so by the first isomorphism theorem, right, because M alpha is sent to M beta via this change of coefficients function. So M alpha goes to 0 under that, and the first isomorphism theorem tells us that if we have something going to 0, then we can mod out by the ideal generated by that. Said differently, really we would want to look at the kernel of f, and the kernel of f happens to be the same as M alpha, or equivalently, the kernel of f contains M alpha, And since the degree of m alpha is the degree of m beta, why is that? Well, iota is just changing coefficients, so it doesn't change any of the powers of t. So if you're degree 5 before applying iota, you're degree 5 after applying iota. Right? So the degrees are the same. So it can't be that we have something of smaller degree showing up here for a variety of reasons. I guess we don't even need to look at degrees here. Actually, let me back off degrees for a second. And m alpha is irreducible. There we go. That's the right thing to say. It's irreducible, so the kernel can't be smaller, okay? Because that would mean m alpha factored, and it doesn't factor. All right, so that's why we get a well-defined map that way, because it is in fact the kernel, and that is the j hat. That's our j hat there. So how can we come up with a j here? Let's do it in purple. So what's j going to be? Well, j is going to be the following. We are going to, let me just do in like dark purple here. We're going to undo evaluating at alpha. We're going to apply j hat, and then we're going to evaluate at beta. Okay. So the desired isomorphism which is going to be a map from K join alpha to L. Let me give myself even more space actually, because we've got a bunch of composites here. We're going to undo evaluating at alpha. We're going to apply the isomorphism j hat. And then we're going to evaluate at beta. I guess I didn't argue why j hat is an isomorphism. Let me just say is a composite of isomorphisms. And then let me just give you a brief argument for why. And this will restricts this, I'll call that j, and j restricts to the function iota on k, because we're not doing anything with the coefficients. So j does to the coefficients what iota does to the coefficients. Okay, let me just say as an aside, I didn't do this. Sorry, this proof's getting, the proof in the books leaves a lot to be desired, so I wanted to be really specific. So j hat is an iso because k is isomorphic to L via iota, and the degree of m alpha equals the degree of m beta. So in other words, these guys here have, well, I'll give you two reasons why it's an isomorphism. The coefficients are isomorphic, so you're not like getting more coefficients, and they have the same degree. So they both have a basis up to, of powers of these alphas and betas up to n minus 1. Right, 1 alpha all the way up to alpha n minus 1, 1 beta all the way up to beta n minus 1. And the function just sends alpha to beta, right? So it interchanges bases. So it's an isomorphism. Alternatively, this map here is actually onto, because again, the coefficients might change, but they change isomorphically. You don't get new coefficients. You'll get more coefficients. The natural quotient from L adjoint T to m beta is a surjection, right? Because every polynomial here comes from a polynomial there. Since the kernel of f is generated by this ideal, the ideal generated by m sub alpha, in fact, the first isomorphism theorem tells us we're an isomorphism onto our image. So that's another way of going about it. So there's two ways. Okay, nevertheless, proof is done. Sorry, it was kind of a long and complicated proof, but nevertheless it's done. Let's see an example of it in action. And this is really, all of mathematics is really just examples. But this example, I think, illustrates what's happening. And this is going to be, again, kind of a long example, so sorry about that. So let's start by looking at the polynomial t cubed minus 2 as a polynomial with rational coefficients. Okay, we have two roots. There's there's three roots, but there's two roots I want to look at. Well, let me just say the roots are the cube root of 2, which we've been calling alpha, omega squared alpha, where omega is e to the 2 pi I over 3. All right, so we have these three roots that we've been playing with since chapter 1, and we're going to play with until the end of the class. Okay, this is a fundamental example. All right, so these are our roots, and we have an isomorphism already that we've been playing with for the latter part of this chapter. There's an isomorphism here uh, generated by alpha goes to omega alpha, right? Cool. Okay, that's going to be our iota. So if we go up here to our diagram, this is our iota, okay? Now, if we allow the cube root of 2, t cubed minus 2 is now going to factor. It's going to factor as t minus the cube root of 2, and then I think t squared plus the cube root of 2, t plus the cube root of 4. Do I believe what I just said? Yeah, I believe what I just said. Okay, so you can just check that real quick. Take a minute, pause, multiply that out. Great. So once we allow ourselves the cube root of 2, t cubed minus 2 sort of is no longer, becomes reducible, right? It's no longer irreducible. Here's the root that we added. And then here is some other part that we're going to find is, the roots of this are omega alpha and omega squared alpha. So in particular, they are, they're not in this field. So this guy is now, this is an irreducible guy. And it has omega alpha as one of the roots. And it has omega squared alpha as the other root. Those are the roots. Great. Now in q adjoint omega alpha, tq minus 2 is also going to factor. Only we're not adding in the cube root of 2. We're adding in omega times the cube root of 2. I'm going to actually leave them as this is like t minus alpha, t squared plus alpha, t plus alpha squared. And this one's going to be t minus omega alpha, t squared plus omega alpha, t plus omega squared alpha squared. All right, cool. So in q adjoint omega alpha, again, our polynomial is no longer irreducible. It's reducible because we added in one of the roots. So this is the root we added. And then the remaining portion is actually still going to be irreducible. So this guy is irreducible with roots alpha and omega squared alpha. All right. So what we're going to do here is we're going to do something really cool and really interesting. We're going to add in one of the roots to q adjoint alpha. We're going to add in one of the roots of the irreducible guy. We're going to add in omega alpha. We're going to add in this one. And then in q adjoint omega alpha, we're going to add in one of the roots of the other irreducible guy. We're going to add in alpha. So remember, q adjoint alpha is k, q adjoint omega alpha is L, and we're adding into k omega alpha, and we're adding into L alpha. All right? Okay, so let's do just that, and let's just notice something. The mapping. Let me formalize what we're going to say. So what we're going to do, because this is complicated, it's always good to be more specific than less specific. What we'll do is add in omega alpha to q alpha and alpha to q adjoint omega alpha. Okay. So the minimal polynomial, let me just write it down. The min poly of omega alpha over q adjoint alpha is the following. It's t squared plus alpha t plus alpha squared. And the min poly of alpha over q adjoint omega alpha is the other one that we found, the other irreducible one, is m alpha of t is t squared plus omega alpha t plus omega squared alpha squared. That's an alpha everywhere. Okay, cool. So let's go back and let's look at the conditions of the theorem. So we have an isomorphism between k and L. Great. What else did we need? We need to have simple extensions. Okay, good. We have those. We're adding omega alpha to one and alpha to the other. And we have to look at their minimal polynomials of these guys that we're adding in. And we have to check that our isomorphism that we started with sends one minimal polynomial to the other. So let's do that check now. All right, so the isomorphism that we started with interchanges alpha or exchanges alpha with omega alpha. So let's check this. Iota hat of m omega alpha of t, what is that going to be? Well, it's iota hat of this polynomial. And what does iota hat do? Well, it does iota on the coefficients. So the coefficient's 1 there. This is an alpha, so that's going to go to omega alpha. And then that's an alpha squared. That's going to go to omega squared alpha squared. That's exactly m alpha. So it does interchange the polynomials. Cool. Cool, cool, cool. So by the theorem, we get an isomorphism we added in omega alpha to this one, and we added in alpha to the other. And this isomorphism, the isomorphism is iota, oops, I keep dotting my iotas, on Q alpha and sends omega alpha to alpha. Right? That was the other part, right? It restricts to the identity on whatever iota does on the base fields, and then it interchanges the new guys that you're adding in. Okay, so it's the regular guy on Q adjoint alpha, and it interchanges the new ones we add in. Okay, cool. One last thing I will say to show you what's really happening in this theorem, and we're going to come back to this a little bit later when we talk about splitting fields. Let's just notice something. Let's notice that actually when we add in alpha and then we add in omega alpha, that's like adding in alpha and omega alpha. And when we add in omega alpha and then we add in alpha, that's like adding in alpha and omega alpha. So these fields here are equal. They're not isomorphic. They are isomorphic, but they're better than isomorphic. They're equal. Okay, they're the same fields. It's like that meme with the office picture where it's the same picture, right? It's the same picture. So what we've done here is we've constructed, this is way cool, okay? This example is just amazing. We've constructed an automorphism rather, of Q adjoint alpha omega alpha that is not the identity. Why is it not the identity? Well, it interchanges alpha and omega alpha, right? It swaps them is what it does, right? It's a swapping function. So it interchanges alpha and omega alpha. So as it sends alpha to omega alpha and omega alpha to alpha. And this is going to later tell us we have a very interesting element of the Galois group of the field extension associated to t cubed minus 2. This example is amazing, incredibly important. Go back through this example a few times because it is kind of complicated.